All right, everybody, come in and sit down. Welcome to plenary session number 2, Human Exploration from a Geologist Point of View. And we emphasize that. I'm Scott Hughes.
And I'm Kelsey Young.
And we will keep you on track. You got 10 minutes to talk.
12 minutes, I think.
12 minutes to talk? 15 minutes total. We will give you a warning at 5 minutes left and 3 minutes left. And then any further than that, you might see somebody stand up with a crook. Okay.
And just a reminder, we do have the discussion section at the end, so if we're short on time, you can save your questions and cover it in the 20-minute discussion block at the end when we'll bring all of our speakers back up here to take any remaining questions. So the first speaker of the session needs no introduction. Dr. Jack Schmitt will be talking about pre- and post-Mare pyroclastic deposits at Taurus-Littrow.
Wow. Thank you very much. It's great to be with you. I'm mainly going to talk about pre because I don't have time to talk about post. And you've all heard that story, or some of you have heard that story anyway, recently, although new developments always arise. Is this going to work today? Guess not.
You could just announce it.
All right, next slide, please. Whoops, go back one. There you go. This is a question that I'm going to talk about mostly. Did volatile release prior to Mare partial melting trigger lithoclastic eruptions throughout the megaregolith? And in our recent, just concluded discussion of Moonrise, I mentioned that this is just another possibility for resurfacing the moon. Next, please. The reason I got into this goes back at least 40 years. It always bothered me a little bit when you think about partial melting from the lunar mantle producing the Mare basalts, which are vesicular. It always bothered me what happened to the volatiles, and particularly the volatiles that would be released just prior to partial melting. And so that stuck in my mind for several decades. Next, please. And I just show that slide because it shows vesicles in the basalts that we sampled at Taurus-Littrow. Taurus-Littrow gave us I'm sure it's not unique, but for the Apollo missions it was unique, opportunity to examine this particular question in that at Station 6 we have essentially an accumulation of regolith since the formation of the valley. And at Station 2, we have regolith that's only been exposed for, depending on who you believe, 70 to 100 million years. And they might be different. And it turns out they indeed are. Next. Next, one of the things that resulted from our recent look at LRO photographs is that there are really two avalanches. There's an old one and a new one. They may be separated by about 100 million years, but Station 2 is circulated on the left and Station 6 on the right. Next. Now, when you look at the measured size frequency distribution of the Station 2 sample, that's the young regolith sample. It's bell-shaped with a peak at about 60 microns. And that's sort of what you expect regolith to look like. But at the Station 6 regolith, you have an asymmetric size distribution with a peak much finer grained at about 16 microns. Next. And next. And this is the difference between the two when you look at the makeup, the reported makeup of the material in those samples. And namely that you have a much higher concentration of plagioclase, clinopyroxene, and orthopyroxene in the Station 6 old regolith at the base of the North Massif than you have at the Station 2 young regolith. And next just illustrates with that arrow that it's roughly compensated for by more breccia in the Station 2 sample. And which has much less of the fragmental mineral debris. Next. Now, I decided, is there any other place on the moon that we've sampled where we might get a little more information about this possible lithoclastic eruption, pyroclastic eruption that would have preceded the Mare? And you may recall that when we went to the Apollo 16 Descartes site, we thought we were going to encounter volcanics because of the smoothness of the Cayley Plains, relative smoothness of the Cayley Plains. Next. And those are the traverses of the Apollo 16 crew, Young and Duke. And next, we have cores from near the lunar module and one core from their station 4. We have other cores, but their data there is not quite so helpful because nobody's looked at it. Next. And this is what you find. At depth, from roughly starting at about 10 centimeters in the various cores, you start to see an increase in concentration of plagioclase, primarily plagioclase. There's not much in terms of the mafic minerals. There's some, but not much. And the one sample that is not, I haven't fully tried to figure out the absolute concentrations. I think I can, but the way it was reported, it's not directly obvious. But the deep core also shows a concentration of anorthosite and plagioclase at depth. And it may be that these cores are showing us that there is a lithoclastic debris layer in the cores that is forming part of the Cayley Plains, as we originally thought. And one note to make is that the maturity index in those sections is significantly lower than the maturity index in the surface regolith. Now, that maturity index data also includes drive tube 68001, but there's no particle information that I've yet found on that particular drive tube. Next. Now how's my time? 4 minutes. Again, I just next want to illustrate that on the Post-Mare pyroclastic eruptions, we also were deriving volatiles. Were being driven by volatiles. Those volatiles almost certainly resulted from volatile reservoirs deep within the moon that had either been unaffected for some reason by magma ocean formation, which I don't believe, but more than likely are from below the depth of the original magma ocean in a more chondritic protocore of the moon. I'm not going to go farther than that. I'd rather take questions on the first part of this, the pre-Mare pyroclastic eruptions, rather than try to repeat things that I said at LPSC just this last March. And so I'll stop there and take any questions you have, or we'll proceed with the next paper.
Well, we have time for some questions right now. Hello? Okay, it's on. Plenty of time for some questions. Anybody?
I guess I can.
I've got one really quick question.
Surely.
What do you think about some of those early pyroclastics being more lithic rich because they're almost like Vulcanian, just release of volatiles that are not truly, forming vesicles, but they're just emanating upwards? I
think that's exactly, they're not, it's the early volatile released as the upper mantle began to heat up again due to the existence of an insulating megaregolith above it. Otherwise, the mantle would not have remelted. It took some other thing to happen, namely the formation of the megaregolith in the crust to provide the insulation that would cause remelting. But prior to actual remelting, as the volatiles released, they would move upward, great density contrast, and entrain the fragments within the megaregolith, the small fragments within the megaregolith, and that's what your lithic pyroclastic eruption was. And in fact, I think there's an interesting reason for the difference between the Apollo 17 lithoclastic material, namely the presence of significant amounts of mafic materials, and their relative paucity in the Apollo 16 material, and that is because there are probably relatively few Mg suite plutonic bodies in the megaregolith or in the crust below Descartes relative to that below a basin like Serenitatis. Does that make sense? Did I get that out all right? Clive, did you have a... Oh, Jim?
Jack, thinking about the venting...
I don't think you have to hold it quite that high. It obscures your beard.
Okay, oh, good. Wouldn't... Can't have that. Full disclosure here. Okay. So just thinking about the venting. So, there are places where we see shallow emplacement of Mare dikes for sure, and maybe even the venting of the surface like you were talking about. So, for example, in Mendeleev, where you have a long crater chain that does not look like a secondary crater chain, it could be venting of the type you talk about at the top of a dike, which is, below maybe a kilometer or so below the surface. So that's... But
that's a dark pyroclastic.
No, not at all.
Basically,
it doesn't vent any, it just vents the gas.
Okay.
So you have basically degassing at the top of the dike, and the foams collapse, and you just maybe get a few pyroclastics, but you can get none at all either, okay? So the question is, going back in time, like you're talking about, to the pre-Mare era, what's the geometry? I mean, if you're generating gas, okay, is it magmatic gas derived? I mean, where do you accumulate such a large amount of gas and then separate it from the magma?
I think it's mostly hydrogen, Jim.
Okay.
And the reason I think that is that if you imagine the initial separation of material from the magma ocean as it formed, it would be immiscible iron-sulfur liquid, iron-nickel-sulfur liquid. That's the first thing that's going to come out of a magma ocean, probably, that originated from a roughly chondritic material originally. And that's going to react with the magma to produce a FeO water or hydrogen, FeO hydrogen mix. And that, I think, is probably the origin of the hydrogen. The water that originally was in the chondritic material would react with that immiscible iron-sulfur liquid to give you hydrogen and FeO. And so that's where I think it's coming from. It's a mixture of hydrogen and water that's resulted from that kind of activity.
Yeah, Jack,
yes.
just thinking about the Apollo 16 site, Chip Shearer had another look at Rusty Rock and started to find, or at least concluded, that this was endogenous to the moon. It wasn't an alteration as during the transit back. And that would conclude that there's potential chlorine gas there as well, as another feature in terms of, now we've started to find volatiles on the moon. We can't stop finding volatiles on the moon. So I mean, it's sort of amazing to see that. But that chlorine then adds another wrinkle to the story in terms of these. He termed it, I think it was a metasomatic type enrichment of rusty rock by this venting, or this fluid, whether it be gas or liquid, but this fluid that went through that particular rock. Is there anything in terms of what you presented here that would lead you to conclude that was not just unique at Apollo 16?
Well, that's a good point, because the only volatile that I'm aware of that's ever been identified within a Mare vesicle is fluorine. And where there's fluorine, there probably was chlorine. And so that would not surprise me that the volatile producing vesicles in the Mare basalts, although it may be mostly hydrogen, possibly carbon monoxide included, but you would expect some small amount of other volatiles such as fluorine and chlorine. So I hadn't thought about it, and I'm thinking out loud now, but it may well be that could be the source of it. In fact, what I really hope will happen, is part because of being stimulated by this talk and otherwise, is that we'll get a consortium looking at the cores at Apollo 16 that have the same set of eyes, or sets of eyes, looking at all the cores and doing the size frequency analysis, the particle analysis, and also begin to do some serious volatile analysis, particularly surface correlated volatiles that might be present in those plagioclase-rich zones. I think there's a heck of an opportunity here to see if we can identify this something that I think almost certainly happened, and that you got some early release of volatiles before the Mare actually began to melt.
Right.
Mare, the proto-Mare began to melt.
Okay. Thank you.
Okay, that's it.